Welcome back 8th grade. In this video, we're going to be looking in your Eureka workbook, Module 1, Lesson 4, and we're going to be continuing our discussion on numbers raised to powers. We're going to continue our discussion on exponential notation, and we're going to jump right into this. So we already talked about all this. This was the last 3 lessons. Go back and look at the videos from the last 3 lessons. Okay, but now we're going to be talking about raising numbers to the 0th power. And just for a basic definition of this, for any, and you're going to write this as I'm writing it, for any positive number x, so for any positive number, we define x to the 0th power as equaling 1. So what this means is that any positive number, take example 3, let's say 3 to the 0th power, what is that going to equal, guys? What did we say that equals? 3, please, to the 0th power equals what? It's going to equal 1. What about a billion? A billion to the 0th power. What does that equal? That equals 1, right? These are both positive numbers raised to the 0th power. That equals 1, all right? And to illustrate why, I'm going to come over here to my paint canvas. Oh, look at this fresh paint canvas with nothing on it. All right. So to begin this discussion, let's talk about bases. So let's just say, for example, we take base 3 again, right? Just for an example, okay? So we have base 3, and let's say we raise it to the 3rd power. Well, what does that equal? That actually equals 3 times 3 times 3. And we could actually work that out, right? 3 times 2 times 3 is 27. But there's also an implied 1 here, right? 1 is a factor in any number. So multiplying this by 1 doesn't change anything. And in fact, it's a factor of this expression. So we'll throw the times 1 in there just to show you this illustration as we go down. Because as we go down, let's say we raise 3 to the 2nd power. Well, what is that? We have 3 times 3. Well, still, the times 1 doesn't change. It's still there. Still a factor. Let's say we go 3 to the 1st power. We talked about this, right? That's just 3, right? 3 to the 1st power, it's just 3 one time. But we can also say it's 3 times 1. Again, 1 is still a factor, still part of it. Well, then what happens when we go down even further and we go 3 to 0? How many 3's are going to be in this expression? They're going to be 0 3's, right? But what's left? We still have a factor of 1. And this is one illustration of why numbers to the 0th power equal 1. So throughout this lesson, remember this rule right here, okay? If x is positive, then x to the 0th equals 1, okay? This doesn't work if the number is negative, and we'll talk about why later. But I want to do another illustration of why x to the 0th power equals 1. And let's use a situation where maybe we have an infectious disease, right? And have you all ever heard, maybe some of you have heard of the term, over the last few months you may have heard of the term patient 0. You may have heard this spread around, okay? Patient 0 is one person, and that's the first person who catches a disease, okay? So patient 0, that's the first person, right? One person has caught whatever and disease we're talking about, right? And let's say for every person infected, they infect, let's just say 3 people, okay? So that first person infected 3 people. So our base is 3. All right, and these represent generation 1. This is our first generation. So base 3 equals 3 to the 1st power in our first generation. Patient 0 was just one person. Generation 1 infected 3 additional people. So from here, we keep going down, and each one of these people is going to infect 3 people. Our base is 3, so each time 3 people are going to get infected. And now this group is in a group of base 3. The base is still 3, but now we're at 3 to the second power, or 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 3 to the second power equals 3 times 3, which equals 9. And you can see this is generation 2. This is the second generation. In this generation, there were 9 peoples involved in this situation. And as we go down, base is still 3, so all these people are going to get 3 more people. So 1, 2, 3, and it's going to go on like that, right? A bunch. Give me a second. Anyway, that would have been impossible for me to draw immediately. 3 to the third power is 27. 3 to the third power is 3 times 3 times 3, or 27. And in my scenario here, this is the third generation of infection. Now, I'm going to do this again, but with a slightly different scenario. This example comes straight from a old Eureka math 9th grade example. And what we're talking about in this one, in this little example, is bacteria growth. Now, for those of you who don't know how bacteria grow, they grow up and then they split into 2 bacterias. And then some time goes by and then those graduate into 2 little bacterias. So it's the same situation. You have bacteria 1, that's your 0 patient 0 or 0 generation. Generation. And in the second generation, that 1 is going to split off into 1, 2. So this is Gen 1. This is your first generation. And again, this is base 2. So 2 to the 0th power on the 0th generation, we equal 1. 2 to the 2 on the first generation, we're multiplied by 2 each time, we're going to get 2. And we keep going. And on generation 2, Gen 2, how many will we have? Well, we'll have 2 to the second power, so 1, 2, 3, 4. And on and on and on. From here, this will double again. Gen 3, we'll have 8. Gen 4, we'll have 16, so on, 32, 64, 128, on and on and on. So those are some examples as to why the numbers to the 0th power equals 1. I'm actually speaking about this live with the top math people, personalities in our parish. And what is being confirmed for me is that this doesn't need to be even a positive number. So I'm going to shorten this definition down for you for any number. So this includes if it is -1 to the 0th power should equal 1, -2 to the 0th power should equal 1. Now my little analogies over here break down if you use negatives. That doesn't work. These don't work if you use negatives, but the rule is actually for any. It doesn't need to be positive. For any number x, we define x to the first power to the 0th power as 1. Here is an operational illustration for why that is the case. Again, it's just like what we did with the 3's, but now they're negative over here. So you can kind of see why even negative numbers to the 0th power equals 1. Okay, so let's move down to some slightly more complicated ways of understanding this. All right, exercise 1. Let's just get into it. List all possible cases of whole numbers m and n, right? Okay, so let's go back. Let's look at what we have here. Remember, m and n are our exponents and all of these rules that we have right here. For identity 1. Okay, so what is identity 1? You gotta look up here. This is identity 1, okay? All right, so we're gonna list all the possible cases of whole numbers for m and n for identity 1. Okay, any possible whole numbers. More precisely, when m is greater than 0, so m is positive, and also when n is positive greater than 0, or it has to be positive. Okay, we already know that one is correct. So we already have been told this, that when m is greater than 0, when n is greater than 0, when they're positive numbers, when these numbers up here, this m and n, are positive numbers, we know that this statement is true. And to be completely honest with you, it's always true. Okay, all right. Exercise 1. What are other possible cases of m and n for identity 1, for this rule up here that we haven't talked about? And I'm going to give a billion bonus points for anyone who can give me what Eureka wants out of this. You guys know I love hanging out with y'all. That was a really interesting discussion of this. If you did something that great. So let's just talk about what Eureka wants us to talk about. So here is the first example, case A, where this identity is also true that we haven't discussed. So again, if x to the nth times x to the nth equals x to the m plus n, right? Okay, that's the position, the identity. Okay. So if m is positive here, m is positive, so m is a positive number. Let's give m a value here. Let's say m is 10. Okay, so we have m is 10 to the 10th power times. And now we're saying n is 0. So n to the 0th power. So we have x to the nth, which is x to 0 in this situation, okay? Now the question is, does this still equal x to the m plus n? Yes. And again, this always works. It doesn't matter what value m and n are. We're comfortable with saying all of these have positive exponents on them, but later we're going to talk about how you can even have negative exponents, and in some situations where you're going to have even fractions as exponents, and even negative fractions as exponents, which you really shouldn't see a lot of. You shouldn't see a lot of either of this, but we're going to talk about it. So here in case A, this is another way that we thought about it that we hadn't thought about it that works. Okay, and here are the other two cases of that we haven't talked about, but it's still true. Case B, if m is 0 now, so this is just the flip of this one of case A. So this time m is 0 and n is positive. Again, it doesn't matter what m and n are. This is true. Right? It's true even if m and n equals 0. So x to the 0 times x to the 0 still equals x to the 0 plus 0. It's still x to the 0, which is 1. We could say we have 1, any number. Let's call x 2, but we have 2 to the 0 plus the 0, just anything to the 0th power is just 1, right? So we have 2 to the 0th power times 2 to the 0th power. That's just 1 times 1, which is going to equal 2 to the 0 plus 0, or 2 to the 0, or 1. So all of these make this true. All right, so this statement right here, we learned this in the last lesson, or the first lesson, lesson 1 in this module. This is always true. It doesn't matter what the exponents are. So let's just take a look at it where this time n is 0, right? So what I'm saying is that this is equal to this right here is the suggestion. Well, let's actually do the math and let's see if that's the case. Okay, so let's have 2 squared. 2 times 2 is 4. Times 2 is 0. What's anything to the 0th power? 1. equals 2 to the second power. Well, is that the case? 4 times 1 is 4. What's 2 to the second power? 4. It works. It works every time. It works if you make m a 0. It works. These work. All right, so look, come to exercise 2. It wants us to check this again using some real numbers, or check to see if it's correct. Look, we did that over there on my paint thing. You can rewind and go check that. But let me just show you why this is the case if both exponents are 0, right? So let's say we had x to 0 times x to 0. Would that equal x to the 0 plus 0? Would that be the case? Well, what's x to the 0? It's a number. Any number to the 0th power is just 1, right? Well, any number to the 0th power is just 1. So 0 plus 0 is 0. X to the 0th power should be 1. 1 times 1 is 1. Does 1 equal 1? Yes. It's always true. It will work. This works. Okay, so exercise 3 wants to check position 2, or the identity 2, the second rule that we talked about. They want us to check and see if this is true now. If we replace m and n with zeros. So that's what we're gonna do. Okay, we're just gonna alternate m and n as 0 respectively, and we'll give the other number some value, right? Let's keep 2. I like 2 as x. We'll keep x equals 2. For this first example, we'll make n equals 0. So we'll have m as, I don't know, let's say m to the third power. And we'll have n equals 0. All right, so in this first example, we'll replace x with 2, m with 3, so 2 to the third power, and n with 0, n to the 0th power with 0. I'm just trying to fix that on the fly. N equals 0. All right, and 3 is ugly, but that's fine too. So let's see if this is still the case. So does this equal, what I'm suggesting is, does this equal 2 to the 3 times 0, which would be 2 to the 0 or 1? Is this statement true? Well, let's try it. Let's work it out. So we'll do what's in parentheses first, 2 to the third power. So that's 2 times 2 times 2, 4, 8. So we have 8 in parentheses to the 0th power. Now, does that equal 1? Well, we're raising a number to the 0th power, right? So is that true? Yes. This statement is still true even if we replace n with 0. Now let's try it in reverse. Let's now replace m with 0 and let's make n equal 3, for example. Okay? So I changed this problem around a little bit to make it to reflect these rules that we're using right here now. Okay? So our base is still 2, only this time we're raising it to the 0th power first and then to the third power on the outside of the parentheses. So what I'm suggesting is that equals 2 times 2 to the 0 times 3 power, or 2 to the 0, anything times 0 is 0. So we have 2 to the 0 power, which should equal 1. So let's check if this is correct. Now let's do this using our order of operations over here, right? So let's do what's in parentheses first. 2 to the 0 power is 1. Anything to the 0th power is 1. Now 1 to the third power is going to get us 1 times 1 times 1. 1 times 1 times 1 is just 1. Does that equal 2 to the 0th power, or 1? Yes, it does. So that worked out. So the last case they want us to check is if it works with both of these exponents being 0. So let's try that now. All right, so here is this situation. Again, just written out. We have 2 to the 0th power raised to the 0th power. Does that equal 2 to the 0 times 0, or 2 to the 0 equals 1? Right, 0 times 0 is 0, so it should be 2 to the 0 or 1. Let's check and see if this is right. So we have 2 to the 0th power inside. So what's that? That's 1. And then we raise that to the 0. What's any number to the 0th power? 1. Does that equal 1? Guys, these rules that they get, I don't know why they wanted us to actually prove this out. All of these statements are true, regardless of what the value of m. M and n could equal anything, and all of these statements are true. They're facts. But in exercise 3, they want us to go ahead and prove it for the third identity. So I'm going to do that for y'all. Y'all can follow along if you want. If you want a copy, you can. I'm not going to make you. If you're just follow me. Okay. So this is the exponential rule we learned in the last lesson. When you have the exponent on the outside, you multiply it by the exponents on the inside. Here we have x and y, which have an implied exponent of 1. N times 1 is just n, so we have x to the n, y to the n. All right, so what they want us to do is prove that this would still be the case if n equals 0. Okay, so let's give x and y some arbitrary values. So let's just say in this exercise, x equals 2, just for simplicity, and y equals 3, just to make them different, positive, simple numbers, just for example. So let's come back, and what we're suggesting here is, let me clean this up a little bit before we go. All right, this is what we're suggesting. This is the position. We learned this rule in the last class. Let's just see if it's still the case if n is 1. So we have 2 times 3 to the 0th power, which we are suggesting equals x, or 2 to the 0th power, times y, or in my case, 3. Oh my God. 3 to the 0th power. All right, so let's work these out and see if that's the case, if these things are actually still equal. So here we have in parentheses 2 times 3, 6 to the 0th power. Anything to the 0th power is 1. So this is equal to 1. Let's come over here. We have 2 to the 0th power, which is 1, times 3 to the 0th power, which is 1. 1 times 1 is 1. So yes, we proved it now. We went through and we proved it for each case, for every time. All of these rules that I taught you in the last lessons are true. They're true. All right, so great. We're going to apply that later on. But what we want to do in exercise 5 is we're going to learn something slightly different. We're going to write in expanded form this number right here using exponential notation. Well, how do we do that? Well, how are we going to do that, Mr. Shaheen? So before we can rewrite this as exponential notation, we need to understand how to write numbers in scientific notation, which is essentially exponential notation. We'll talk about scientific notation. So here's what here is the next assignment I'm positing to you. The next question I have for you. Who knows what this number is? Could you tell me what this number is? Give it a second. See if you could come up with a name for it. Okay, y'all are silly. Okay, so first of all, let me just give you the name for it, just because this is fun. This is irrelevant to the lesson, but this is actually 3 septillion, and we count it by the groups of zeros. So the first group of zeros tells us thousands. This is thous. Then you got your millis. Anything after this comma is a million. Then anything after this comma is a billion. Anything after this comma is a trillion. Anything after this comma is quadrillion. Quad, for those of you who know a little bit about Latin, quad, it's the 4th, right? So this one is going to be quintillion. So anything after this comma is quintillion. Anything after this comma is sextillion. Sextillion, 6. Anything after this comma is septillion. So here we have 3 septillion as a number written out. But one thing you might notice about this big old number here that we have it's not really pleasant to write, right? Now, what I'm suggesting to you is that there are 3 septillion atoms in our universe. Who knows what atoms are? Atoms, they're the smallest thing that make up matter, right? So this is just a big old number. This is a big old number to represent a huge quantity of something, right? Now, if you're a scientist, you don't have time to write this out all the way. That's a big number. Why would I want to write that number? So I would want to write this in scientific notation using exponential notation. Okay? The way I would write this is I would write it as 3 times 10 to the 1, 2, 1, 2, 3, 4, 5, 6. Golly, how many numbers are there here? 9. How many zeros are there? 10, 11, 12. How many? 13, 14. Jesus, I shouldn't have done this. 16, 17, 18, 19. Golly, 21. Oh, I should have paused to do this. 23, 24. So there are 24 zeros behind here. So that means we're going to raise this to 10 to the 24th power. Now, for those of you who know what happened when you multiply something by, what happens when you multiply something by 10? What happens when you multiply like 10 by 10? What happens? You're just throwing that 0 behind there, right? 4 times 10, you're just throwing that 0 behind the 4, right? So what if we continue this? What if we had 10 times 10 times 10? Well, what happens? Well, you're just adding another 0, right? You're just adding another 0 behind 100. So you're going to have with the 3 zeros. So 1,000 equals 10 times 10 times 10, or 10 to the third. So a simple way to write certain numbers, especially really big numbers with a lot of zeros like we have in the septillion, right? We don't want to write 24 zeros out, so we can just write 10 to the 24th. And that saves us. And if we multiply it times 3, that's telling us that it's 3 septillion. 3 times 10 to the 24th. It shortens that statement for us, okay? All right, so now how does this apply to writing a number like this in exponential notation? First of all, it probably doesn't. If you're a scientist, you have enough time to write this out rather than writing this out. This is actually not as short as this. But let's actually write this out in exponential notation anyway, okay? So what we have here is 8,000. We have 8,000 plus 300, 8,000 plus 300 plus 70 plus 4. So what we're going to do is we're going to take each one of these values and rewrite them in scientific notation. So here we have 8,000, so we could write that as 8 times 10 to the third power, because there are 3 zeros here. Now, again, if you're a scientist, you wouldn't do that, but that's fine. We're writing. We're doing this. You're doing it. You're doing it with me. 3 is the first number we're looking at. How many zeros are there? 2. So it's 3 times 10 to the second power plus 7 is the first digit. How many zeros? 1. So we write it as 10 to the first, or you can just write it as 10, but since we're writing in exponential notation, why not? And then we have 4. So we write that as plus 4. We could really just write it as plus 4, but if we wanted to write this in exponential notation, we would multiply times 10 to the what? To the what power? To the 0 power. Because 10 to the 0th power is 1. 1 times 4 is 4. So this would be how you write that in exponential form. Okay, I want you to try exercise 6. It should do this with this number now. Okay? God, 3 minutes because it's big and we're doing it, so do it. As always, ladies and gentlemen, thank you for your participation. So you should have come up with something like this right here. So first you take the 6 million, you convert it into 6 times 10 to the 6th. There are 6 zeros. 6 is the first number. So you're multiplying 6 times 10 to the 6th power. Excuse me. Okay. 90,000, 9 is your first number. How many zeros are there? There are 5. That is your exponent over the 10, so 9 times 10 to the 5th. Same thing, there are 4 zeros here. 8 is our first digit, so it's 8 times 10 to the 4th. 5,000, same thing. 5 is the first number. There are 3 zeros. Now, so that is the straightforward way that goes, and then we start here, where this gets a little confusing, right? What's the first digit in this term? Like, look right here, up here, we have 0 in the hundred spots, right? So we have 0 hundreds. 0 is your first number, and you're multiplying that times 10 to the second power, which it doesn't matter because anything times 0 is just 0, right? If I were writing this in scientific notation, I wouldn't even bother with that. But this is exponential form. That's fine. We did it. If you didn't add that, that's fine. 60 is straightforward. 6 is your first number. You're multiplying it times 10, and you want to put to the first power here, but if you didn't, you're not wrong. But then we get to 2 again. 2 is being multiplied times 10 to the 0th power. Fantastic. If you put just 2 there, 2, it's fine, because you could have just had plus 2, and that also would have been correct. Okay, good. Thank you for your attention this afternoon. So you're going to come down to the problem set, all right? Now, the problem set is going to have a mixture of the rules that we use throughout this week through lessons 1 through 4. Okay, so you're going to need to apply all of the lessons that we've learned for just these 5 problems. They're just 5 problems, okay? So do your best. You're going to simplify as much as possible, right? You're going to get to a point for some of these where you can't simplify them anymore. Don't sweat trying to do your best. Check your rubric for how to respond to Eureka math problems. Remember to show your work. Yeah. And I'll see y'all in the next video. Thank y'all.